plasma volume. Or let's say extracellular volume. But we know we're talking about plasma. And after dehydration, we have L2. So this is what? So supposedly, if we had in this, if the sodium level, if the concentration of sodium is 40 milliequivalent of sodium, when there was no dehydration, right? And then we have water. This is now we have lost maybe the entire volume is also 200 mils, and now we have lost 40 mils. So we have now what? 160 mils versus the same 40 milliequivalents. So you have what? You have the same, the decrease in volume, but the same. So supposedly this is going to be lost. This is going to be more concentrated before. So, but if we lost a little amount of this, it can cancel. There's no change. So when sodium is lost together with water, then it's going to be isosmotic. And then if we have isosmotic, will there be fluid shift? Will there be fluid shift?
No.
The answer is no. So in a situation where we have hyperosmotic, where the plasma is, we have lost, there's too much loss of water without sodium, you have a hyperosmotic. And then hyperosmotic, a situation where there is what? This water is lost and sodium is also lost so badly, right? Whereby more sodium is almost, it's not proportional. When sodium is lost in excess together with other electrolytes, even though there is dehydration, but there is excessive loss of sodium, so it becomes hyperosmotic. So we're going to be looking at what happens. So let's take it one after the other. Let's take it one after the other. Hyperosmotic. Let's isosmotic. We have said that there will be no change. So let's just be describing them. Since we have understood it now based on the numerical values, let's just describe them. If this is isosmotic, if this is isosmotic, what is going to happen? Isosmotic dehydration. The fact remains that the volume will decrease. So there is going to be a decrease in volume. Now the concentration is also has no change, right? There's no changing, and then there's not going to be any fluid shift. So what is going to happen for the fact that is described as dehydration, there's going to be a decrease in volume of the ECF. That is the only thing that will happen. No fluid shift, no change in concentration, and then, but if you have hyper, let's say hyper, plasma is now hyper. So there's a decrease, this is the original value, but now we are talking with L2. We are dealing with L2, and then there's no sodium loss. So it is hyperosmotic compared to this. So what will happen? Water will move from here to dilute it, right? If this was the original volume of water, this is filled up. By the time water moves here, we have this one, L2. Does that make sense?
Mm-hmm.
So there's going to be, and as this one continues to, as water continues to do if this was the L2 during the hydration, we're going to have what? L3. It's going to increase. Isn't that? As water moves from here to here. So first of all, characteristics of hyperosmotic, Yes, there is decrease in, primarily, there is decrease in what? Volume of the plasma. 2, there is increase in osmolality of plasma. In response to that, fluid shifts from ISF to plasma. Decrease in the volume of, are you following? Decrease in the volume. Then as this decreases in volume, what happens to its osmolality?
It's going to increase.
It's going to increase. Good. So it's still going to increase its osmolality. In response to its increase in osmolality, water does what? Are you following? And if this was the original volume of water, eventually it will become to what? L2. So there's going to be decrease in what? Cell volume or cell size, as the case may be. So if we don't correct this problem, please look up. That is the danger of the dangers of continuous dehydration. If we don't correct this problem, this cell will do what? Will shrink badly. Because the size, it will continue to lose water. It will continue to lose water, and that is the ultimate aim. The aim of this challenge going on here is to cause disease, or to cause ill health, right? By compromising cell function, right? So anything can cause this. Anything can change this. Anything can cause it, for whatever reason. All right? But the fact remains that blood is being lost, water is being lost, electrolyte is also increasing in the body. So the impact it's going to have on the body is the cell will start dying. And that is disease. That's ill health. But affecting different organs. And then these organs is going to shut down. So now the question is, we don't want to go into several causes, things that can cause this. So anything that can cause this, as may have been listed somewhere in the slides, will lead to this condition. So now let's look at hypo. Let's look at hypo. Plasma is now overdiluted. Hyperosmotic dehydration. What happens? Let's fix it ourselves. Fix it. Because when it comes out in the exam, you don't need to cram. You just, using your scratch paper, you just draw it, and then you see the answer.
If water flows.
Good. So water is going to go this way. So you now can imagine this is going to swell, right? It's going to swell. So, and if it swells, so this one is already dehydrated. So the consequence, there's a different, is already dehydrated. So decrease in volume, increase in decrease in volume, decrease in electrolytes, and that's why it's hypo. Water moves here. So what happens to here? 1, increase in volume, right? Decrease in osmolality, right? Are we following? There is an increase in volume of the ISF, decrease in osmolality. So it's now becoming more hypo compared to this, right? Are we following? So water continues to do what?
Continue to move to the ICF.
And then the cell does what?
Swells.
And don't forget, before this cell swells, don't forget that whether fluid is going out of the cell or fluid is coming into the cell has already been challenged. So it doesn't have to wait until the cell shrinks or swells. For the fact that there is a change in fluid dynamics already compromises cell function. You get the point I'm trying to make? So it's not as if, okay, let's allow it until you get that point. Once that scenario is created, the cell is already at a loss. Alright? So, of course, no disease starts today and kills the animal tomorrow. Unless if it is a very high virulent virus or bacteria and all of that. And in most cases, it doesn't happen like that. So, it will always give room for the body defense mechanism, immune system will start fighting, trying to help itself and all of that, of course, comes to a point where the animal comes to the clinic and will help. So it doesn't, but we should appreciate the fact that some kind of adverse condition is going on, some kind of challenge is going on. So that's how it happens here as it relates to this. So we have just mentioned, so now in hyperosmotic, I'm not bothered about this. That's why I say the causes will be listed, but that's not my thing. I don't want to bother you with go and this is not pathology, right? So, but this is what I want you to understand. That's the physiology, right? So that's what we have shown. The same thing goes for